Okay, perfect. Yeah, no, thanks for the introduction, Robin. Really appreciate it. I'll give a few more words on what this is about on the next slides. But for me, I am as Robin mentioned, recently retired from the oil and gas industry. And that leaves me free to give. It's not that I wasn't free to give my opinion before, but when you're in a big company, there's always some limitations in terms of what you can do in external presentations. So to give a general overview to you all is there's an opportunity to do that now. So I wanted to do that. So this is a fairly irreverent talk about the oil and gas industry. There are no, I'm not sort of revealing any shocking secrets or anything like that, in case you're hoping for that. But what I am going to do is give you a very quick overview of kind of some of the interesting aspects of the industry. What I'm not going to do is try to convince you of anything. We all have opinions about oil and gas. In terms of its usage or the fact that we shouldn't use it, and that is perfectly okay. I'm not here to change your mind. I'm just here to talk about some interesting aspects of it from sort of a technology and a sort of a process point of view. And to make that really clear, I'm to narrow it down. I'm going to only talk about upstream oil and gas, as mentioned in the talk and title. And so you can actually see the oil and gas industry is typically broken up into upstream, midstream, and downstream. So upstream is actually finding and producing the oil. Midstream is like pipelines and storage. Downstream is the refining and petrochemical manufacturing. I spent my 25-year career in oil and gas in technology, upstream technology specifically, really on the geosciences side. More than anything, but with a broad overview. I spent a lot of time in the business as well on both exploration and production. And I left for a whole variety of reasons. One of which is a general increasing discomfort with the industry as a whole, and kind of where it's going. But that wasn't the main reason, I should say. One thing I will tell you is I'm going to give you a very, very broad overview here. Each one of these slides is not only its own talk in and of itself, potentially, you can get a degree in pretty much any one of the slides on here. So I'm really skimming the surface here. That said, if I ever say anything that people don't understand, if you've got a question about a term I've thrown out, or anything like that, please just let me know. Because if you're thinking it, somebody else is thinking it, don't hesitate to interrupt me presenting. That's not a problem at all. I'd rather you have an understanding of what I'm trying to say, rather than feeling like you might interrupt. And a piece of advice there in the lower left that I always give people who are new to giving any kind of talk is this quote here: a good talk really isn't about making yourself seem smart, it's about making your audience smarter. And I think particularly academics should take that to heart all the time when giving a presentation. And my goal here today is to make you smarter about what oil and gas is, what it means, and to give you some helpful thoughts about it along the way. Okay, so let's dive in. So first step to oil and gas is finding it. You have to find oil and gas through exploration. And there's four big parts of that. There's source, reservoir, seal, and trap. This is just like the basics of oil and gas. So source, you need the oil, right? So oil actually comes from organic rich rocks. Can you all see my pointer, by the way, when I'm moving it around on the screen? Does that work?
Yep. Yes, it
Okay,
does.
perfect. Great. That's a little helpful. So on the source side, you basically have organic rich rocks that have to be cooked to just the right temperatures and some pathway for that oil and or gas to flow up through the rocks. And one thing to be aware of that many people are not is that all of the subsurface, every rock you find on the subsurface, is completely saturated with fluid, typically water. So when you generate oil or gas, what it's going to do is it's buoyant, right? It's less dense. Oil floats on water. It's going to start moving up towards the surface of the earth. And so anytime you generate oil or gas, it's going to try to bubble up to the surface no matter what, because it's less dense than the water that saturates everything else. So what happens is then you basically need some container to hold it in, and that's your trap. And inside your trap, you have to have a reservoir, and a reservoir is a porous rock that contains the oil. And the trap is some sort of geometry that allows it to keeps it from bubbling up to the surface, which means you need a seal over the top. I'm going to talk a little bit about source and a little bit about reservoir, and I'm more or less going to skip seal and trap because those are fairly obvious, although they're their own worlds of stuff, particularly traps. But we'll stick with source and reservoir for now, just to give you a sense of what's going on. So source rocks. So what are source rocks? Those of you in the UK might know about the Kimmeridge clay or the Kimmeridge shale that's there on the coast of Dorset on the sea cliffs. And this is a rock so rich in organic matter that you can actually set it on fire. So there's actually quite a few instances of this cliff catching on fire because it's basically really has generated, it's so organic rich and has generated essentially almost all of the oil and gas in all of the North Sea all comes from this Kimmeridge clay from the Jurassic. And so, these shales look like this. You might be used to seeing shales if you ever looked at rocks. Shales are dense, black, layered rocks that are typically laid down in the bottom of the ocean. Not always, but most of the time. So these are like deep water, not a lot of sand or anything coming out. It's almost all organic matter, stuff raining out from the ocean and dying and falling to the bottom, and a little bit of clay. And that's what gives you shale. And so I put these, I know everybody likes to read slides, so I put these little comments in here, which are little sort of tidbits and thoughts that I might want to hit or that you can read yourself. And so this one is, if you can light your pet rock on fire, it's likely either a source rock, good source rock, or probably not a rock at all. So how do you find these source rocks? Well, now we're going to get into a little bit of the technology behind this and a little bit of the mystery and challenge of all this. Well, remember that oil and gas likes to seep up to the surface of the earth. So if you have an active source, then one of the things that can happen is it may fill up a trap, spill over the trap, and continue up to the surface. Doesn't always happen, but can happen. And when that happens, you get a natural oil seep. And all the earliest oil fields in the world were found by somebody finding oil on the ground somewhere and then going and drilling. In fact, the earliest oil seeps known, there were some in Italy that the Romans used for greasing axles in carts and things like that. They used the asphalt that came up to the surface there. This is an image that's very typical of what's done in oil and gas, where there's some outlines of some traps that people think are in the area, and they did some very early work to note that, okay, over this particular area in this outline, they found some oil seeps on the surface of the ocean. This is off the coast of Namibia, a very big discovery that was made earlier this year and last year. People have been looking for oil and gas off the coast of Namibia for decades, and Shell and Total, I think, made a big discovery there earlier, just a few months ago, about a year ago. And the way we find these seeps on the surface and the way you get these weird maps of all these squiggly lines is actually synthetic aperture radar is the most common way to do it, because when you put oil on the surface of the water, it actually damps out all the little wind waves on the surface, and you get a very sort of, let's say, transparent spot, or not transparent, but a very featureless spot on what is otherwise a very cluttered radar image of the water. So it's easily identifiable from synthetic aperture radar, and that's what's used to map these things out. And you can see here from the Caspian Sea, these little squiggles are all oil seeps. The outlines here are oil or gas fields. And one of the things you can see is that it's not necessarily a direct correlation between where the seeps are and where there are oil and gas fields. You see there's a bunch in here where there don't seem to be any. And that sort of makes sense if you think about it, because these may be leaking away from the traps. They may be coming out somewhere else, whereas it's actually trapped in the areas where there's oil and gas. But it's a good sign that you actually have oil there, because there's plenty of places in the world without oil. So if you've got oil seeps, you have oil, and you might have the opportunity to find it. So, kind of the point here is that you might find a seep, and you find it on the surface of the ocean, But if you think about currents and wind and all that kind of stuff, knowing exactly where that seep came from is a challenge. But people have gotten pretty good at this, actually, and going back to the original seep on the seafloor, even in incredible water depths. And they actually go and sample the oil from those seeps. And there's some neat things you can do with that oil that people are probably not aware of. Oil is made up of, crude oil is made up of just all kinds of stuff. I mean, we think about all the components like gasoline and kerosene and jet fuel and all this stuff we refine it from, but it's actually this whole mess of organic compounds. So there's one in particular that I just want to highlight for you called oleanane, and I could be mispronouncing that one. You know, it's a triterpenoid, oleanane, and I think cholesterol is another triterpenoid. These are like really complicated polycyclic aromatic compounds. But what's neat about oleanane is oleanane was effectively unknown to the Earth until about 100 million years ago, sometime in the Cretaceous. And you can actually see this. This organic compound, there were no organisms that made oleanane until 100 million years ago. And what happened 100 million years ago is angiosperms, flowering plants evolved. So there are no flowers at all before 100 million years ago. And flowering plants are what make this molecule. And that shows up in the oil. And that also tells us a lot about the oils. It tells us about the environment that it came from. It tells us potentially what age it is, like here. And there's dozens of these different molecules that have evolved over time. And it's really kind of a fascinating study into evolution and thinking about how this stuff got preserved, and all that. And this also sort of, many people have in their head that oil comes from dinosaurs. And of course, having these molecules in it tells you that this was not made from dinosaurs. This is mostly made from plants. It's a lot of marine plants, a lot of marine organisms like plankton and things like that. Because remember, a lot of the shales are from the bottom of the oceans. So you do get pollen and stuff being swept out, and that's the source of some of these molecules. But it's amazing that we can still see things that are like plants' versions of cholesterol from 100 million years ago. It's kind of astonishing. So it's kind of a neat thing. And the way you do this is you throw this stuff into a gas chromatograph and a mass spectrometer, and you get these all of these different peaks that tell you that you've got this molecule, and you have hundreds, if not thousands, of different molecules in there. And sorting that out is its whole own profession and thing. Really an interesting area. So now we're going to go from source rocks to reservoirs. So source rocks are what make the oil, reservoirs what hold the oil. And I know many people have in their heads that is not an uncommon view, that when you drill a well down into the surface of the earth, you actually go into a cavern underground, and we produce oil or gas from like big underground caverns. Don't feel bad if you've had this view, but it is entirely wrong. That is not what happens in almost every case. Where we do actually find oil and where we produce it from is things like sandstones. So this is just sand, like from a beach or from a river that's been bound and compressed into a rock. And limestones. You may not think of limestones. Most of the limestone you've probably seen in your life is used in building materials. This is in fact from a wall. But it tends to be quite solid. But most limestones have all kinds of pores in them, all kinds of holes, lots of porosity, like you can see in these ones in the wall. And it's that porosity, either in the sand, the gaps between the grains, or the holes in the limestone that actually hold the oil. So when you're producing oil or gas, it comes out of all of those tiny pores in the rock. It's not a cavern at all. The one thing that the reason why these images exist and why this is a real thing is this is salt down here. And one of the things that is done is people actually will drill a well into salt and pump a bunch of water in there and make a cavern in the salt. And then they can use that cavern for storage of chemicals, like including oil, later. This is actually a pretty common thing that's done all over the world where there's salt. So you do get those. That is a real thing, but it's not actually where we find oil and gas. There's one more source of pore space that'll come up again later in the talk that's really important for oil and gas. I'm going to start asking questions in this, so feel free to unmute. Anybody know what that another source of pore space is? I'll give you a hint. It's actually in one of the pictures here. Any guesses? You can put it in chat if you want. I could probably bring up chat. Any ideas? Any idea what that third pore space is?
Heat?
Yeah. Sorry, what was that?
Heat?
Matt, I couldn't quite hear you what you're saying.
I was saying, is it peat or like
Oh,
compressed
peat.
soil?
Yeah. Well, peat is more of a source of oil and gas. Yeah, that's a good one. But actually, Robin's on it in chat. Fault lines, and in fact, not so much faults, but just fractures. You see how the sandstone is fractured, and if you look at the sandstone, the biggest place where you're going to have space in the sandstone is actually in the cracks generated when this is fractured. So those fractures can actually hold quite a lot of oil and gas. Just natural fractures that happen in the rock. All right, so how do we find it? How do we find reservoirs? The biggest way we do that is seismic, and seismic is its own fascinating thing. And boy, there's a lot of research into this and all kinds of stuff. But basically, it's quite simple. You set off a source of shock waves, sonic waves, and the goal here actually is to have really low frequency waves. The best sources right now send out as low as 1 hertz of frequency sound, which is almost, it's infrasound, right? Because you need that sound to penetrate quite a lot of the earth, and you set up this long string of receivers in this case in the form of hydrophones, and you actually record the echoes from what's happening underground. And they use these absurd looking ships like this one that looks like the front half of a ship with all these lines coming off. And each one of those lines is a whole line of these hydrophones. And these can be like 10-kilometer long. These are called streamers. And you can imagine the logistics of trying to run this ship around, and it's almost like mowing the grass. You're going to turn it back and forth across a big area of ocean, and trying to turn those streamers around, 10 kilometers of streamers around behind you in such a way that you need them straight when you're collecting data is a bit of a nightmare. And there's a lot of engineering and work that goes into collecting this on the surface. And so one of the things that's happened in seismic is people said, well, I don't like that anymore. It's actually much better for technical reasons to put the receivers on the bottom of the ocean. So this is called ocean bottom nodes. And so it's an independent little unit with a geophone in it to record the sound, and some memory and a battery module. And to give you an idea of the scope of this, to do this properly, you actually need to put the entire array of nodes down on the seafloor, which could be at a ridiculous water depth, like 3,000 meters of water, which is which is almost as deep as the Titanic. You put them down on the seafloor. The battery needs to last like 6 to 18 months. And you need about 4,000 of them to cover. And to put a node down, you send an ROV down. That's what's in the picture here from an ROV vessel. You have to send an ROV down, a little remotely operated submersible, to place this on the seafloor. And then when you're done, you need to go back and pick them all up because they don't transmit any data back. That's all recorded on the module. So you can imagine this is an incredibly costly exercise to do this. There's a lot of work being done to try to figure out ways to simplify this. One of the ones that I was involved in my last days in the industry is a little Norwegian company called iDrop. And they have a very clever thing, which rather than using an ROV to place one of these nodes on the seafloor, they have these sort of bomb or torpedo looking things. You chuck off the side of a boat and they have little fins on the back. It navigates itself autonomously down to the right spot to about a couple meter circle. They pop out some legs, land, and then when it's done, it drops some ballast and the thing comes up to the surface and you pick it up. So you don't have to have the ROV to go down and put it down and pick it up. You just have a bunch of these on the surface that you can pick up. If that works, it's actually an enormous savings of cost because you don't need that ROV to go and put things down. Tons of really interesting technology go into collecting this data because it's so essential to oil and gas and what's done. And the reason why it's so essential is it gives you a picture of what's going on in the subsurface. So these are a couple pictures actually from the British Antarctic Survey, who have done a lot of seismic data collection. And the imaging continues to improve with computing and processing techniques and all kinds of really interesting acoustic stuff. So old data might have been lower resolution. Newer data is higher resolution. You can see more stuff. And if you look on the cross section, this is actually like a 3D volume of data, which is what you get out of this. And you can see there's this big sort of transparent zone, which is a big channel that's cut into the rocks and filled probably with the sandstone. It might be a mud. It's hard to say from here. And you can actually map all of that out in 3D. And energy companies spend an incredible amount of manpower doing this kind of interpretation and pulling this out. So there's a huge frontier of research in terms of AI interpretation of this that is really interesting. This data, it's a bit of an art to interpret and to understand, but more and more, and the more detail you can see, the more you can actually pull really interesting detail. You can actually see another channel coming off this way on this data. Really interesting stuff. But again, you can get a whole degree in this, so I'm just getting right over the top of this. Sometimes you get really lucky with the seismic data. Sometimes it looks like this. And what is interesting about this is you can kind of see that these are all the layers of the rock, right? And there's something going on here, which is a fault. I can tell you that. There's a fault that cuts down here. And you can see that the layers of the rock actually continue to be more or less parallel to all of this. So what is this? Anybody have any ideas of what that big booming reflection might be that cross cuts the rock here? Any ideas? Any thoughts?
Is that the water that you talked about?
Yeah, you're very close. Very close.
Is it the interface between oil and gas?
Yes, that is, or between the oil and water. So oil and water and gas have different acoustic properties, or they change the acoustic properties of the rock when they're there. So you can sometimes, if you're really lucky, get a reflection of the boundary between gas and oil or oil and water in the subsurface, which is a really good sign that you might have all the elements that you need. You've actually got a source that's creating this. You have a reservoir that's got enough to actually cause this acoustic change. You have a trap, and you have something sealing it in. So sometimes you get every component of what you need to feel confident about a discovery before you drill it. There's a thousand ways this can go wrong. People have drilled things that they were sure were oil that turned out to be like carbon dioxide charged water and all kinds of stuff. But it's sometimes it's that easy, but it's almost never that easy. To give you an idea of the economics here of drilling an offshore oil and gas exploration well, the typical probabilities of success in somewhere like the Gulf of Mexico is we've done all the research. We think we understand what's going on there. A good probability of geologic success, which means you have all those components, is about 40%. The chances of it being a commercial discovery, something you can actually make money on, about 20%. And the cost of drilling an exploration well in the deepwater Gulf of Mexico right now is about $120 million. So I don't know about you, but I would probably hesitate to put $120 million of my own money down on something with a 20% probability of success. And companies are obviously a little bit hesitant to do this as well. So they try to distribute this risk down as much as possible. So you might come up with the idea to do this, but you don't want to put all your money down on that. You develop a partnership where everybody shares in the cost and everybody shares in the benefit. And what that means is you can drill many more wells. And if you only have a 20% chance of success, you can distribute that opportunity of success across many different wells. And so that's really a common way things are done in the industry to decrease the risk. So after you've found some oil and gas, or when in the process of finding it, you have to drill, right? This is the very unfortunately named Deepwater Titan. Boy, I'd hate to have that name for a ship, because it's not the Titan that sank in deep water at the Titanic. This is the Deepwater Titan, which is a 8th generation drill ship. I could not tell you what differentiates a first, second, third, and so on drill ship, other than it's just they drill into deeper and deeper water effectively. So this is one of the most modern ones that's out there. It can drill in a maximum water depth of about 3,600 meters, which is astonishingly deep. That's I did the math. It's 0.96 Titanics deep, and it can drill to a depth below that line, below there of 12,000 meters deep, which is astonishingly deep. So that's 3.2 Titanics not. So the 3.2 Titanics deep. So, you know, these are also quite expensive. They're a big part of what goes into the cost of drilling a well. And so if chartering a yacht is not posh enough for you, the day rate on one of these is about $250,000. So if you don't want to sail around in an expensive mega yacht, you can just sail around one of these and claim you spent more money. Okay, I will try to pay attention to the questions in chat. Robin's got one. How deep do these oil wells tend to end up being? The reason why they build these with a particular depth is there is usually an economic reason to go that deep. So people are chasing deeper and deeper water and deeper into the earth. But typically, the deeper you go, the worse the situation is in terms of the rocks. So everything gets more compact, more tight. There's less pore space for there to be oil. It's more expensive. So your chances of both geologic and commercial success go down. So there are places where you want to drill deep, but very rarely do you have to drill that deep. You do sometimes have to drill horizontally quite far, and that comes up fairly often these days, and we'll get to that in a little bit. Long reach wells can be 10 kilometers long. It's one of the longest wells ever drilled was a 10-kilometer reach well from the origin point. So drilling, drilling is absolutely not for the faint of heart or the wallet. This is a fairly complex. Oh, sorry, go ahead.
Second. There's two other questions just before we move on from seismology.
Yep.
Ed's asking how large are these nodes that go on the floor?
Oh, I'm sorry, I missed Ed's question.
Philip's asking how far apart are they and how big an area would 4,000 nodes cover?
Yeah, so you can probably get a sense of how big this node is. They're sort of people say sort of briefcase sized. They're not huge. They can be smaller than that. They can be bigger than that, depending on how much battery they have on there. They would typically, if you're going to cover 4,000, drop 4,000 nodes down. You know, let's say you have 100-meter node spacing or something like that. So that gives you some sense of 100 meters is probably way too short. You know, you'd want to cover tens of kilometers by tens of kilometers to hundreds of kilometers by hundreds of kilometers area with these nodes and distribute them around. And there's some play back and forth between how much does it cost to do it versus what quality of data you want to get and how big of an area you want to get. So it's always sort of a balancing act there of what you try to do. Hopefully that answers your question, both for Ed and Philip. Yeah, so it's a little bit, sorry, Philip, it's a little bit how long is a piece of string. It really depends on what you're going for and what you're trying to measure there. So jumping back to drilling, this is a fairly complicated diagram, but it is really important. And it's good to understand this because this is the crux of drilling. You don't just drill a hole straight into the earth for several kilometers because it simply doesn't work to do that. And the reason why is if you think about it, as you go deeper, the pressure will change, right? So you'll have more and more pressure, just like in the atmosphere as you come down or down in the water as you go, you get more and more pressure. It's the same. It continues down into the earth. You still have that hydrostatic pressure. And this is made a little more complicated by the earth itself being complicated. So there's a prediction of what that pressure is at depth, and there are boundaries to that pressure. And so what those boundaries are is there's something called the pore pressure gradient, which is how much pressure you would need to force fluids, have fluids come into the rock or out of the rock, right? And then on the other side, there's the fracture gradient. So if you have too much pressure, then you will actually fracture the rock. And so what happens is you have this window that changes with depth between the red line and the blue line. And if you look, if I started at something that was below the blue line and I wanted to drill, what I do is when I drill a particular hole, I use a weight of mud to stay in this zone. So the column of drilling mud that's in there, so you inject mud down into the drill bit and it brings all the cuttings back up with it as it's cutting, but it also prevents fluids from flowing into the well. Because if you have fluids like oil or gas flowing into the well, and you drill into like a gas deposit, right, you're going to have gas uncontrollably flowing into the well, which means you have gas uncontrollably coming up to the surface, which means it's going to catch on fire, cause a blowout, all of those horrible things. And so what you have to do is you have to drill at something below this fracture gradient down to a point where you're just above the pore pressure gradient. And you can see this casing point is set here. And what a casing point is, you drill a particular hole size, a big hole, and then once you've drilled that hole, you run a metal casing in, a tube of steel. It's a big steel pipe that's just a little bit smaller than the hole. And then you pump cement in, and you fill up that space between the outside of the tubing and the outside of the hole, so the gap, so this is like caulking in the end of your pipe. And then what you would do is you'd send a smaller drill bit down and drill a smaller hole in between here. And what that allows you to do is change your step again and change your mud weight and continue to go. And so you actually have to do this multiple times to get down to your reservoir interval. And so you end up with a whole series of steel pipes of smaller and smaller and smaller diameter. And at some point, you can actually run out of casings if you haven't planned well and you have unexpected things, and you have to start all over again because you've run out of room. Basically, you've run out of casing points, and you need to start with a bigger one. There's all kinds of stuff that can happen. In both cases, yeah. So the question is, what is the rough diameter of the holes? The big one on the outside, which is called the conductor, right at the seafloor, is typically like 24 inches. And then there's a whole standard of sizes. You step down to 17-inch, 14-inch, et cetera. And they're all basically designed. It's one of those things that is still imperial all over the world. They still use non-metric sizes for all these drill pipe sizes for whatever reason. Every casing does reach back up to the surface. No, I'll show you that on the next diagram. You'll see in just a minute. You definitely don't, because that would be a waste of thing. Yeah. So gradient PPG I did not say it because I didn't want to dive too deep into this, Matt. But it's pore pressure gradient. It's effectively a pressure with depth kind of thing, and a weight. It's probably too complex of a subject to get into, but just think of it as your pressure is the best way to do it. So you're basically your pressure gradient is changing with depth is what's happening here. So both of these situations. So if you go below this line or above this line, it's bad news, right? So if you go below this line, and your pore pressure of your rock your pore pressure of your mud is less than that of the rock, you have that flow of oil and gas into the well, and uncontrollable flow back up to the surface. If it goes over this line, you fracture the rock, and if you think you've got a whole column of drilling mud above this, and you start fracturing the rock because of the weight of that column, you start losing mud into the rock. And on those drill ships, you have a finite space to hold mud, right? To hold the material that you use all kinds of stuff to weight up this mud, like barite. The question is, what is drilling mud? It's a mix of all kinds of stuff, and it's basically tailored to get exactly that density you want to weigh the entire column to balance this chart is what you do. So it looks like mud, but it's got barite in it. It's heavy stuff to weight it up. It's got all kinds of stuff in it. It's a mix of different things. You have water-based mud, oil-based mud, depending on need. And that's its own school of stuff in drilling engineering. If you go below this line or above this line, it is an urgent situation. Everything stops until it's fixed. And if it's allowed to continue, then you will result in uncontrolled flow of oil and gas to the surface. And that's a blowout, and nobody wants that. Very dangerous situation, and it's bad news. So you've got all this steel pipe down here, and you've definitely got steel pipe in the last hole that you have. Okay, yeah, Phillips saw that. You have this last hole cased in steel, but you actually want to get to the rock outside of it. So what you do is you make holes in holes. You have a tool you lower down into the well called a perforating gun. And it's actually, you can see this is actually a perforating gun here. And you can see these little cylindrical things on the other side, which unfortunately I didn't photograph well, but those are little cups that hold shape charges. So these are literally high explosive shape charges. I think they're usually C4. And what they do is they blast a hole in the side of both the pipe that's carrying them down. This sits within a pipe like this, and the outside pipe, steel pipe here, so that you can access the rock through a very specific spot that you have chosen. So that's perforating. You actually have to blow a hole in this. This is the only like non-military use of shape charges that I'm aware of. I'm sure there are many more, but it's interesting to see stacks of shape charges up in these trailers when they're drilling a well. Okay, so just real quick on drilling. I probably need to hurry up a little bit to finish on time. This is, so the question of the pipes, and do the pipes go all the way down? The answer is no. And you can see it here that you basically have different sections of pipe only covering the interval that's relevant, and cement that's pumped down to seal in the end. Sometimes you can do a bad job with that cement. And if you do a bad job with that cement, you can have gas flowing into the outside of a well. And if that happens, and you don't have like an extra seal on the outside of the pipe you've lowered down sort of later, this thing, you can actually have that gas flowing all the way to the surface, which is a very bad situation. Remember, oil and gas flowing to the surface without you controlling it is bad. And so if you chose, for example, to only put one seal at the top here, instead of a seal at the top and a seal at the bottom, very bad things can happen. So in fact, one company chose to do this this way on the right, and that is one of the things that led to the Deepwater Horizon, the Macondo blowout and fire, and the deaths of the people there. This is bad. Redundant safety measures like having two separate seals is generally a good idea when consequences are high, which anybody who works in high consequence things knows that redundant safety factors are important. So I'm not saying they necessarily did it wrong. They had successfully done this many times, but this time it was not successful because several things went wrong. The cement job was bad, apparently. And there was also a breach in the seal or the pipe here at the top. So multiple things already failed. But having an extra safety bit in place there might have prevented this. This was more the standard. This is a way to save a little bit of money, and it ended up probably not saving very much money in the end, and also costing some lives, which is horrible. So drilling, we talked about how expensive that is to drill a well. Once you find oil and gas, you go into production. You want to turn it into production. Now the costs really get high. So you've probably seen many figures like this with all the different kinds of oil platforms that exist. If you're in shallow water, you can just build a big steel tower and set it on the ocean floor. Mostly, we're finding stuff in very, very deep water these days. And so you have these more sophisticated ones for deeper water. This is the most common one these days. And I'll show you one of these in a minute, these floating production systems, which is just like a giant ship that sits out there all the time, mostly. The cost of this is expensive. The cost of a development solution is typically more than $1 billion for a modern offshore field. This is Johan Sverdrup, the big giant field recently discovered 10 years ago, 12 years ago off of Norway. The cost of developing this phase 1 and phase 2 has been about $15 billion so far. To build all of these platforms, get them in place, get it and drill all the wells they needed, put it in production. For comparison, that's about 0.63 of NASA's SLS project so far, which has been a very expensive project with lots of cost overruns. And this is shallow water. This is only 115 meters of water. So these are actually just steel, just like this one, fixed platforms going right down to the ocean floor. So that's a cheap thing, but it's quite big and therefore quite expensive to develop. What we do most commonly now, or what the industry does most commonly now, is especially in ultra deep water, is FPSO. FPSO stands for floating, production, storage, and offloading, which it does exactly what it says on the tin. It floats, it produces the oil and gas, it stores the oil and gas, and it offloads it. So a tanker can pull right up to the ship and have the latest production transferred to the tanker goes off to a market. The big advantage of this is you don't need any facilities onshore. So if you're in a place without any infrastructure, no pipelines, no nothing, you don't need any of it. You park one of these and you're done. It does everything you need to do. It can also disconnect and sail away if there's bad weather. It can unplug from all these wells, sail away, come back. And this is important in places with icebergs or hurricanes or, any kind of bad weather. So in both cases, there are lots of places we find oil and gas that are, have unstable weather or politically unstable. So, not having the onshore facilities means there's very little for to worry about in the country. There's not a bunch of fixed facilities there. If you did steal an FPSO, which I'm not recommending that you do, but I would guarantee that would get you a mention on the Infra Club Heist channel on the Slack. Just putting that out there. You don't actually need a platform these days. This is a really interesting solution that Equinor originally developed in Norway, and Shell has now taken over, which is the Ormen Lange gas field, which supplies something like 20% of the gas to the UK. I don't know what the numbers are right now. Philip asked a question, if an FPSO unplugs and sail away, could another FPSO come along and plug in the same well and steal the oil? Maybe. That's possible, but you'd have to really know what you were doing in order to make that, because there's sort of design stuff baked into the FPSO for the right pressures and things like that you'd want to make sure you have the right kind of FPSO, or you would have a bad time. This solution, all of this stuff sits down on the seafloor and it's connected by pipelines to shore where there's a gas processing plant. This is actually really neat because there is no platform. Everything is put down on the sea floor in about 1,000 meters of water, which is pretty deep. They did all this construction work with ROVs, so remotely operated bulldozers and all kinds of stuff, and it's entirely unmanned. And this is really the frontier right now in facilities, is if you can put everything on the sea floor, and if you can do unmanned platforms or unmanned platforms. Everybody loves that, because sending people out into the middle of an ocean by helicopter to sit on a metal platform in bad weather filled with flammable liquids and gases is just generally a bad idea. And nobody wants to put people in harm's way, and they would prefer that there be nobody out there. It's also fairly costly. So if you can automate this and put it all on the seafloor, then that is actually preferred. So there's been a bunch of development work to try to make this as both unmanned as possible and on the seafloor whenever possible. The downside, of course, is it's harder to recognize when something's gone wrong if you don't have people there to say, hey, it's gone wrong. It all needs to be censored up. You have to rely on it. And it's also harder to get there to fix when something does go wrong. So there are consequences to that. So one of the things you see a lot, and this is where some of the education comes in a little bit here, is here's the headline from the Namibia discovery I mentioned earlier from the Orange Basin. 11 billion barrels of oil, big blaring headline. So what that is, what that number you see, 11 billion barrels, is an oil in place number. That doesn't mean very much to me. And I will explain to you exactly why that is. Oil in place is simply the volume of rock in your trap times the porosity, so that's a percentage, and the oil saturation, because there's always a little bit of water in there with the oil, and so there's only a certain percentage of oil. Let's say it's 95% or 90% oil, so you lose some of that the volume to water as well. If you think about rocks, and take a sandstone. You guys have probably seen sandstone cliffs. This is not a uniform tank of stuff. It's got sand grains of various sizes, different materials, and remember the oil sits within these pore spaces. And here it's sitting, this is actually carbon dioxide, but there's water and that sort of thing in here as well. I want you to do a thought exercise right now. So if I gave you a cup of wet sand and poured a cup of water into it and put a straw into it, and then let you pump or suck the water out, how much of that water do you think you would get out of the cup of wet sand? Would you wouldn't get 100% of it, right? Because you're still going to have wet sand at the end of it, right? A lot of it gets bound up in these residual saturation. So you get these little bits of water sticking sand grains together that you really have trouble accessing, right? So this is what we do in oil and gas is you're putting a straw into wet sand and you're trying to pull, or oil saturated sand, and you're trying to get the oil out of it. And you definitely don't get all of it. Any guesses in chat as to how much oil we typically get out of an oil reservoir when you find it? So if you started with that 11 billion barrels, how much of that was likely to come out? Yeah, a couple answers in chat, 30%, 48%. That's actually on the high side. Most fields are about 20 to 40%. And if you think about this, it depends on a lot of things, right? So if you've never seen crude oil, there's a wide variety of crude oil. It goes from a very light liquid that's almost water-like in terms of viscosity to something that is super goopy and really thick. So let's do the thought exercise again. If I gave you that cup and it was filled with honey, put honey in there instead of water, how much of that honey are you going to get out? Well, something viscous like that, it's a lot harder to get out. You're going to get a lot less. The rocks matter too. So the rocks, as I mentioned, the sandstones are not uniform in any way. They're made up of all kinds of different layers and things. They are anisotropic. That means it might flow better horizontally than vertically. They're heterogeneous, so they're mixed up with all kinds of stuff. And so if I gave you a cup that had gravel instead of sand, like lots of big pore spaces, you'd probably get more out of it. What if I gave it silt? Well, you probably get less, right? If it was a mix of gravel and silt, so it gets complicated, right? And that's exactly what's happening here. And that's what sets these recovery factors, is what kind of rock it is and what kind of oil it is. And so if it's gas, right, if I put nitrogen in the cup and ask you to get out, you'd probably get more, right? You can probably get a higher recovery factor out of that. But one more thought exercise. So what kinds of things could you do? If I gave you this cup of honey or a cup of water, what could you do? Matt says stir it. You could do that. It's awfully hard to stir rock in the subsurface, but I applaud the thought there. Any ideas for what you could do to get more of that liquid out of this cup instead of just having wet sand? Yeah, pump in heavier liquid, mercury. Yeah, in fact, that's one of the ways they measure some of these things, is they do in mercury capillary injection for measuring things. Vibration's a good idea. I mean, there's a whole bunch of ways you could potentially get more out of it. How do you make fluids less viscous? Maybe one hint. Yeah, soap. Actually, that is a real thing. People do inject soap for all kinds of stuff. You can, bubble gas through them. Yep, that's another thing. Oil is actually, gas is dissolvable in oil, so you can actually change the viscosity and change the properties, and it actually flushes the oil out pretty well. Solvents, yes, solvent injection is a thing. Almost anything you can think of, people have tried it. So if it's honey, one way you would get more out of it is you made it hot, right? If you made it hot, you reduce the viscosity of the honey, and you can probably get more out of it, right? So there's a whole bunch of ways to do it. And just to give you a sense of this, this is the honey version for heavy oil, ultra heavy oil, like the Canadian oil sands. This is pretty much one of the few places they do this, is you actually generate steam and you pump steam down in one well, and it sort of heats up a volume of rock around that, and the oil, sort of this very viscous oil, then drips down into your production well, and then you can produce it that way. So this is called steam assisted gravity drainage, because you're heating up a volume of rock, and then gravity is allowing it to pull it down into this well. The other thing you do, the one of the things that was mentioned, is putting gas in there. The other thing you can do is put water in there. And this is actually a very simplified diagram of what's called water alternating gas. You can do water injection, which is very common. You can also do gas injection, which is common. Less common is doing both, alternating. And the advantage of so what water does is, water is more dense than the oil, right? So water will flow down to the bottom of your reservoir and push the oil up. Gas is less dense than oil, so it will flow to the top of your reservoir and push the oil down. If you do both, you're kind of squeezing it out and pushing more of this oil out into your production well. So this is very common. There's also something called SWAG, simultaneous water and gas injection. And I thought this might be a great or terrible name for a band, swag injection. Yeah, I could go both ways on that. So let me know what you think. Other ways you can get more recovery factor out of the ground. So remember our frac gradient, right? If we push too hard on the rock, we fracture it, and that's a bad thing when you're drilling. But if you already have a cased off well, and we're not worried about uncontrolled flow into the well, we already have pressure control at the top and all that stuff like that. What you can do is you can pump fluid down into the well at higher pressure than this fracture gradient, and this is on a vertical well, and it'll create a fracture, which is sort of an elliptical shaped thing in its simplest form. They're more complicated than that, and you're basically increasing the area of rock that you're accessing with your well. And so you have a bigger surface for that oil and gas to flow into if you create fractures in it. And this is a technique that's existed for a long time. I think since the 50s or 60s is doing that. The other thing that is very common is you increase the area in which your well is hitting your reservoir. So you're increasing the amount of space you have from just the well itself, not from fractures, but from the well is in contact with your reservoir, means it's easier. So imagine instead of one straw in your cup of sand, I gave you 10 straws and you could put them all in. You'd probably be able to get more of that water out of the wet sand. And that's in fact what people used to do. Many of you have probably flown over West Texas and seen this sort of arrays of field. This is back in the old days of drilling only vertical wells. Every single one of these spots is at separate vertical wells. And this is the only way they had to increase their reservoir exposure and get more oil out of the ground, was simply drill more wells. Nowadays, we do something different, which is to drill horizontal wells. So this is the quite famous Troll West field off the coast of Norway. And what's weird about Troll West is it has a lot of gas in a very thin zone of oil and kind of crappy reservoir. It's low porosity. It's not very good. And so to get that out, the only thing you can do is drill these ridiculous wells, which are sit within that very thin layer of oil and maximize the reservoir exposure by having all these branches called a multilateral well, or deviated. This is the place where they drilled the 10-kilometer long well. And this is what a typical development looks like there. This is what Troll looks like. You have a platform in the middle, and then all these umbilical lines to these things on the seafloor called templates. And all the wells actually come from the templates. So when you drill a well, you park a vessel over the top, and then you drill this long horizontal from there. And very rarely comes from the platform itself in these bigger developments. And so this visualization I really like, because this is true scale of how long these wells are superimposed over the city of Bergen, and Troll is just off the coast of Bergen. So it's a nice juxtaposition here. And this is actually truly what all those wells look like. The diameter of the wells isn't really right. You wouldn't be able to see them, but the length of the wells is correct. And how much area is actually being covered in the reservoir by wells is absolutely astonishing. And that gets Troll West all the way up to 52% recovery factor, which is astonishingly high. But imagine the cost of drilling all of these wells to squeeze that a little bit more out of the reservoir. Okay, we're running out of time, so I'm gonna finish up here in a few more slides with unconventionals, right? So now let's go to something completely different. We got our source rocks that are filled with oil, and we need to cook those and flow that up to our trap and our reservoir up here. Remember all that stuff? What if we had a different idea? Since we can drill lots of wells and horizontally, so we can cover a big area and we can fracture them, maybe we could produce a little bit of oil from truly terrible rocks without much pore space at all in them and hardly any mobility. So if I were to drill into the Kimmeridge clay, which is full of oil, maybe I could squeeze a little bit of that oil out of it. And people had this idea, particularly once they were done with an area and had produced most of the oil and gas. They're like, there's still a bunch of oil down in the shale. What if we could drill wells and get stuff out of it? You don't do that first because it's more expensive, right? It's more expensive to drill lots of these wells. You have to frack them, all of these things. But if you already have the infrastructure in place, the marginal costs get lower to do this. So if you already have a bunch of oil and gas development previously, doing this kind of thing can make sense. And so people started doing this. And what you do is you drill a long horizontal well through your crappy reservoir. So the shale is typically the source rock for the reservoir. So often it's deeper. That's not always the case because it can be complicated, but typically you want to drill in the source rock, which is below where you've previously found the oil and gas fields that you've developed previously. But what happens when you do that is you need to make lots and lots of these fractures. So you're going to take each perforation cluster. Remember those holes that we poked in the steel pipe, and fracture it. And so this is a multi-stage fracture where basically you do these over and over and over again against a long horizontal well that stays within here. And so you're making a huge area in contact with the reservoir to compensate for having a really crappy rock, right? Like a shale or a very tight sandstone. And this is unconventionals. So if it's not quite bad enough where you can actually get something to flow from it, you have to pour a bunch of money into it to do that, which is why it's not the first thing you do. But it is a very much an opportunity to squeeze more out of it. But how many wells do you need to do this? Well, remember we showed you this earlier from all these vertical wells. This is from the Bakken in North Dakota. So this is underneath the Missouri River. Every single one of these black lines is a horizontal well. So you can actually see this entire area is effectively covered with wells. So they start from individual origin points like here, and all of these individual horizontal wells are drilled out because you're only going to be able to produce from the small area right around the well with the fractures that you have made from the well. That you can't produce further away from that because the rock is too bad. You can actually see the pressure drop here as a simulation of it. There's whole bunches of area that you're just not even going to be able to drain even between the wells. And so to access that, you need to drill lots and lots of wells, and that's to get some sort of unknown but incredibly small recovery factor, like 5 or 10% at most, out of these reservoirs. It really is an astonishing number of wells that it takes to do unconventionals. And I'm just going to hit this point really quickly. Is you can ask which one of these has a bigger impact on the surface, doing all these vertical wells, and we can see the sort of scarring of the ground that happens from doing this, versus something where the entire subsurface is covered with wells. In fact, it's easy to make the argument. This is the satellite view of this area. You don't actually have as much impact from these unconventional developments. You can see this cluster of wells right here is all these well pads, and they actually extend out quite a long way from well pads that are right along the road. You don't have to dot the entire countryside with well sites. And in fact, out here, this is all wheat farms, and these wheat farmers would not like it if they were building anywhere else but along the roads and out in the middle of the fields, because then they'd be able to produce less wheat. And they actually like their wheat more than they like their oil in North Dakota. So they wouldn't really stand for this kind of thing, but this is actually less impactful on the land. That is not to say it is not impactful. But it is less impactful, less than you might think. And so, which is worse for land use? I don't really know the answer, but here's a case where there's an old oil field right here with all those sort of distributed wells, vertical wells, and then you can see some unconventional development here on these strips. So these will have long wells extending out from each one, whereas all these dots are just vertical wells. And you sort of concentrate the construction and well pads into smaller areas, and you leave, big areas untouched when you do this unconventional development. The reason why companies like it is even though it's very expensive to drill these wells, this is what it looks like to do a massive multi-stage frac job. This is an entire fleet of pumping trucks to get the pressure and volume you need to fracture those wells. I mean, it's an astonishing array of equipment you need to pump down into this. The difference is you can do this and bring this well into production in weeks. If you find an offshore thing and you have to build all of this stuff, that takes years. I mean, 3 to 10 years to bring a offshore facility into production. And so here you spend a bunch of money up front and it costs a bunch of money to keep going. You spend some money up front and you spend basically operational expenditure, but you get your money back quick. Here you have a lot of money up front that you don't see back for years, and oil price can change and that sort of thing. Yeah, Ed's got the question about access rights. Yes, people and companies own, they do get paid, they get royalties. People, if you own the mineral rights to the land in the US, they will come and lease the mineral rights from you and give you a royalty from that. So a lot of these farmers, they still like farming wheat and they still farm wheat, but man, they have gotten really wealthy off the oil, but they still love farming wheat and they will continue to farm wheat. And the question of how deep it goes, what rights you have, it really depends on the contract and state in the US, and then also different by country. So like Canada, you lease from the crown and you lease by depth, not by over an area. It's all very complicated. So it's a complicated answer to that. So companies like this, because they can get paid back quick, they do like this, but this is sort of more risky in its own way because you don't know what's going to happen over that 3 to 10 years of development. This is why one of the reasons you saw this big boom in unconventionals, even though the cost of doing it is more expensive than doing this overall. Okay, so just a couple last points before we finish up. I know we're kind of a little bit over time, more time than I wanted to spend on this, and I don't want to keep you very long, but I wanted to tell you what you should be concerned about with unconventionals, because people get up in arms about fracking. And fracking in and of itself, doing the fracturing is something that's been done for decades, and it can be done. It's normally done safely. There's not really any things that go wrong with fracking. You should not be concerned about it contaminating drinking water, creating earthquakes, things like that. That's not to say that unconventionals does not have those potential downside, but it's not the fracking itself that's the problem. It's typically disposing of the water that comes from the production, both the fracking and the production of the oil and gas. Because when you produce these things, you don't just get oil and gas, you get water, and a lot of water, and you have to dispose of that water down disposal wells. You definitely don't want to dump it on the surface. It is really crappy, salty water with all kinds of nasty stuff in it. You need to drill a well and dispose of it. And so this, basically what you do is you drill a well that's very much like an oil and gas well. You pump the water down and you are fracturing the rock. You're doing all that stuff to pump as much, fluid into it as possible before it can't take anymore, and then you move somewhere else. And that is the process that can create earthquakes. It can contaminate groundwater if done improperly, much more likely than a multi-stage frac job. And so often in places where you've heard issues about this, it is about the regulation of disposal wells that is the big thing you should be concerned about. The companies themselves don't do this. They contract it out to other companies. The big oil companies typically don't operate wells themselves, so that it can disposal wells. And those other companies, especially if not regulated well, can have really crappy practices. And that is a big concern with this entire thing. It also takes a lot of fresh water to do these fractures. This is not great when it's in short supply. And then the impact on the surface, like, for example, wear and tear on roads from all this fleet of trucks that have to be all over the place, is real. And parts of Texas have had real consequences from that. So I'm not here to tell you that unconventionals is great. It's all rosy. There are real problems that can arise, particularly when regulation is poor or money isn't coming back into the community in regards to the infrastructure damage that can be done. So final comment on infrastructure before I end. Infrastructure is always led by what's cheap. We don't like to believe that, but it's true. Even the stuff we get misty-eyed about now. So the red brick universities, so that's a picture of University of Liverpool, the Ivy League in the US, these are all these beautiful brick buildings. They built them from brick because brick was cheap, and it was cheaper than the masonry that was used to build universities previously. We like them now because they look cool and we love them, but they weren't built for us to think they look cool. They were built because it was the cheapest building material available at the time. And they were looked down on at the time because they were not made of masonry like solid structures. And in fact, the whole Ivy League was about making the sense of permanence by planting ivy, giving you the sense that these are old buildings by making them look like they're overgrown with ivy, because they're not masonry. So I don't know if many of you like the 99% Invisible podcast. They had a whole thing on LA recently called Pave Paradise, which is about the parking regulations in LA and the choices LA made to be car centric as opposed to public transportation centric. And it's important to recognize that that was made in the context in the 20s and 30s when the LA basin, which is one of the most prolific oil basins in the world, was producing oil at a ridiculous rate. So this is the production curve from the LA basin. And you see from 1910 to about 1940, it was just absolutely producing billions of barrels of oil just in LA. So gasoline was dead cheap in LA. And so it was a decision at the time to make it car centric because cars were going to be cheap for decades. This also drove Hawaii to build oil burning power generation because there was so much cheap oil available from LA, which is the closest source of energy for Hawaii, that they're oil burners now, and it's still oil burning power plants in Hawaii, which is one of the reasons Hawaii has some of the most expensive power in the US because of that choice made in really the 30s and 40s based on this decision. I'm not going to fault these people for making that decision because it seemed like the right decision at the time. You don't really think 100 years in advance when you make these decisions. You base it on what's cheap now. The good news here is if we look at the marginal cost of power generation, and this is sort of the latest numbers, this is how much it costs to generate a gigawatt of electricity. And if you look at the very cheapest things on here, so the more expensive things. So if you look at gas peakers, nuclear, coal, and gas is generally the cheapest way of conventionals to produce power. Below that, wind, utility scale solar are now cheaper than gas for generating power. Infrastructure is always led by what's cheap. You hear people say, oh, no, that's not true. It's only true and if it's subsidized. Nope, this is unsubsidized numbers for power generation. At least when it comes to power generation, the cheapest way to do it right now is through renewables, photovoltaics, and onshore wind. If infrastructure is led by what's cheap, this means that we should expect to see a continuing explosion of these, even without any kind of government subsidy or intervention, because it's always led by the market. That has consequences in terms of, you know, the challenges of maintaining power when the wind isn't blowing and the sun isn't shining. Then you need battery backup and all those things. I'm confident we'll be able to resolve those things. And this is not the end of the oil and gas industry because transportation still looks very different than this in terms of costs. But I think it's a real sign of what's to come in terms of the infrastructure we should expect to see develop now and what we will see in the coming future as those prices get even cheaper, because they will. Oil and gas is not going to get cheaper. Coal's not going to get cheaper. Nuclear, maybe, but it's really expensive right now. It's almost cheaper to put up solar photovoltaic as it is to build a nuclear plant. So nuclear plants are great and all, and nuclear is a nice source of non-polluting power if you build it safely and properly, but it is still very expensive compared to other things. So I just want to leave you with that thought before I finish, and that's all I have. I've got a few minutes for questions if people have questions and are still willing to stick around to do that. Sorry I went so long, but hopefully it was interesting.
No, thank you, John. That was fascinating. I think we all really enjoyed that. So yeah, if anyone's got any more questions, please type it into the chat, or if you want to, you can unmute and speak your question out loud. Yeah, go ahead.
On that last graph, what were the diamonds in the ranges?
Yeah, I didn't go into incredible detail when I saw it. I was just trying to find an example of the latest. It's hard to find comparisons of the cost of power generation that aren't just renewables, but also include the conventionals. I think those are specific projects that are cited. I can already find it. By the way, I didn't mention this, but in each of the slides, there is a link to where I got the image from. I like to cite the sources. I like to show you where I got it from. And so there's a link to each one of these. So that one actually does have a link to that, and I can bring that up and see what the footnote says for example, number 7 there. It says, so like one of those has a footnote. So like the gas combined cycle is very high. It says it represents the cost of the observed high case gas combined cycle inputs. Oh, with green hydrogen. Okay, so that one, some of those include some other technologies and some other things. And on the low side, it would be inclusive of some other costs in terms of decommissioning and that sort of thing. So there's some very specific things that those diamonds represent. I'm happy to send the link. I'll drop the link of the graph in the chat so you can have a look yourself. It's probably the easiest way to do it.
I've got a quick question if no one else has got a question at the moment, which is how do they actually drill these holes? Like you were talking about potentially like 10-kilometer long or at least multi-kilometer long holes going at all sorts of strange angles and depths and trying to presumably get into exactly the right bit of rocks. How do they even tell where the drill head is, let alone control it to drill in a crazy angle?
Yeah, as mentioned, every single slide in here is its own entire talk. And that is its own entire talk. They use basically like MEMS accelerometers in it to know, it's like an inertial guidance system in it, because obviously there's no GPS or anything in there, and that's how they know where it is. And there's lots of ways to sort of push what's behind the drill bit is a whole bunch of technology. There's a bunch of sensing tools, which include those accelerometers. There's ways to sort of push the further back on the drill bit or further back on the drill string against the pipe to sort of curve it around in a certain direction. There's just all kinds of stuff that they do to make that happen. And it is actually a pretty fascinating bit of technology in terms of how they do that. If you think about having a 10-kilometer string of pipe, this is a drill bit on pipe is what they do, because the fluid's pumped down from the middle of it. And at that length, the pipe is like spaghetti. It's like a big floppy thing. So it's astonishing that they can do this and really get those wells to drill at 10 kilometers.
I remember reading something recently about how they get the data back from the sensors on the drill head, and I'm pretty sure somebody mentioned like infrasound and things like that. It was quite crazy, I thought.
Yeah, they use very low bit rate pulses, acoustic pulses in the mud itself to transmit data back to the surface. And most of it is stored on memory in the well, in the sensors there. But they do get some of that back with pulses in the mud. There's a lot of stuff on wired drill pipe in terms of trying to get high bandwidth connections down to the drill bit, but it is very slow right now, most often.
Could you just talk briefly about you talked about the dangers of having uncontrolled oil and gas coming up the pipe up the well? Is the way that you control it when you actually want to get oil and gas up the well just by having those tiny little perforated holes at the bottom and just making sure they're tiny little holes and you control where they are?
But no, because when you're drilling, you basically have an open hole at the top, right? You have to have an open hole because there's no way to seal that off in any kind of reasonable, rational way, because you need the mud flowing through there. And so as long as you got the mud flowing through there, there's some path for fluids to come out of the well. There has to be for the mud to work. You can't have a sealed system. Once you have a well drilled, you put down a production tubing after you perforate and all that, and you have this whole thing at the top called the Christmas tree, which means you can just turn the well off. You can close a valve and it's off. And that's it.
That just stops the whole pressure. Even if you've got oil under a lot of pressure under there, you can just literally turn it off.
Yep. You can't really do that on top. If you've heard of a blowout preventer, this is a big valve that sits on the seafloor if it's offshore. And what it does is it actually has shear rams that cuts the casing. So if you have an uncontrolled situation and you have no choice, shear ram cuts the casing and creates a valve that just shuts off the top of the well. And it has to cut through, lots of steel in order to do that. And it doesn't always work. And it also means your well's ruined at that point. So it's not a button you want to hit unless things are really out of control.
What sort of pressures are we talking about? Like, do you actually, in a steady state, does it like naturally flow to the surface? Do you have to pump it out?
It depends. There are reservoirs with enough pressure to naturally flow to the surface. Yes. How to get it out from the ground? If you've seen the old nodding donkeys in Texas with the pumps, that's actually a pump, an electric powered pump that's bringing oil up to the surface. You can have downhole pumps. There's something called gas lift, which is really common, which you inject gas down into the oil below, and in the well, and it makes it buoyant enough that it can come up to the surface in an easier way and flow faster. There's 100 ways to get oil out of there, but yes, initially, particularly, it will flow on its own, and late in life, you'll need to give it some support. Is typically how it works.
We just have one more question on the chat. Do the drill bits get retrieved when drilling is complete before production starts?
Yes. Normally, you wear out a lot of drill bits in the process of drilling a well. There's lots of things that can go wrong in that process where you lose stuff down the hole. They normally will go and try to fish it out. But they will pull everything out because it's not so much the drill bit they're concerned about, it's the pipe. So they have a lot of expense imagine what 10 kilometers of steel pipe costs, and it's like chromoly steel. It's expensive stuff. They're individual sections that are machined, they're screwed together as you go down. They really want to get that pipe out. They don't care so much about the bit, but they want the pipe out. There are cases where it gets completely stuck, and you have no choice but to cut it off and try again, which is another horrific thing that happens when you lose an entire drill string. Thanks, Matt. It's a good space. I've been very happy to have it.
Great. Just before we finish up with any final questions, I just want to reiterate what I said at the beginning. If anyone here feels like they could give a similar sort of talk, it doesn't have to be as fancy. The slides don't have to be as good. But on anything interesting that they've done or doing or places they've been, please do post in the Infrastructure Club Talks channel on the Slack. We'd be very interested to help facilitate that, and I'm sure people would really enjoy it. So please have a think about that if you're in a situation where you might be able to do that.
And if you have questions you want to ask, feel free to ask them on the Slack as well. Just ask me anything you want. I'm happy to try to answer anything I can. And hopefully you see I'm trying to give you honest answers here. I'm not in the industry anymore. I have no agenda here. This is just the realities of the situation. We don't have to get into the morals of using and finding more oil and gas because I'm not in that industry anymore. You won't offend me or anything like that. So ask anything you like.
Great. Thank you very much. So if we can all give a virtual round of applause to John for that, whether you want to just clap when we can't hear you or use one of the reaction emojis. Thank you very much, John. That was fascinating. So thank you for giving up your time.
Okay, I'm just glad you weren't bored.
I don't think any of us were bored. I think knowing people on Infrastructure Club, we were all absolutely fascinated by it. And I'm sure there'll be many questions coming along on Slack shortly. Thank you very much.
Lots of shiny technology. All right. Thank you all very much. Have a good evening.